Okay, so let's go ahead and solve this real quick. You can do this the long way by flying up the bit chart, then crossing over, then coming down the byte chart if you want. Go ahead.
I got the number right. I just wasn't sure of the conversion.
Sure of the conversion? What do you mean?
Gigabytes to I wasn't sure.
Kilobits to gigabytes.
Yeah, I wasn't sure.
Well, I'll look at it. So you can either walk all the way up the chart. So we have 65,535 kilobits. So the next thing would be bits, right? So that's times 1,024. That gives you bits. Then you need to get over to bytes. So you divide by 8. Okay. Then you need to get to kilobytes. So you divide by 1,024. Then you have to get to megabytes. So you divide by 1,024. Then you get to gigabytes. So you divide by 1,024. .0078, blah, blah, blah. Okay. Similarly, you could jump columns right off the bat. So you could say 65,535 divided by 8 immediately get you over to from kilobits to kilobytes.
Wait, really? Huh.
Then you divide by 1,024. That gets you to megabytes. Then you divide by 1,024, and that gets you to gigabytes. 0.0078, blah, blah, blah. Same number.
Yeah.
Make sense? Either one's fine. If you don't like doing the shortcut to just jump the column by dividing by 8, or if you're in the byte column, you have to multiply by 8, right? So make sure you're doing the jump the right way. If you don't like that, you can do the long-winded version. Just drive up to the top, cut across, drive back down. It's fine. Doesn't matter. Whichever way makes the most sense to you. Correct answers done the long way are way better than incorrect answers done the short way. Make sense? And that same logic applies to writing code. I think I even mentioned that last time, that I'd rather you write code in a way that makes sense to you than something that matches the solution I have in class. It's going to be pretty common once we start writing programs for you to spend a lot of time on your assignment. Come to class, you might even have a correct answer, but it was just like this voyage that went in all these twists and turns and stuff like that. You see the answer in class, it's like 3 lines of code, and it makes perfect sense to you. Don't necessarily go out of your way to try to write code identically to what I might write in class. Sometimes I'll show you 2 or 3 different solutions, 2 or 3 different approaches to the same thing. I promise you, over time, as you become more skilled, you'll naturally write more efficient solutions to stuff. Much, much, much rather have accurate, inefficient code than inaccurate, I guess, efficient. He's efficiently wrong. Don't be efficiently wrong. Be inefficiently right. All right? But with any work in here, always, always, always show your work. At the end of the day, I don't necessarily care. If you get the right answer here, I'm not going to take off points because you didn't show your work. But if you get the wrong answer, you can give me anything to work with to give you partial credit. Make sense? So if you show your work, I can see like, oh, he multiplied by 8 instead of divided by 8. One little mistake and the entire number's off. I'm going to still take off points, but it's going to be a 75 instead of a 0. See what I'm saying? So do yourself a favor, show the work. All right, questions about this? Make pretty good sense? Go ahead.
Why are we dividing by 1,024?
Because that's the scalar on our chart here. Everything is, so a kilobit is 1,024 bits, a megabit is 1,024 kilobits, a gigabit is 1,024 megabits. On this side, you have a kilobyte is 1,024 bytes, a megabyte is 1,024 bytes, so on and so forth. So it's always a scalar of 1,024. And specifically, we are dividing here because our original number is in kilobits, right? So to go from kilobits to bits, I need to multiply by 1,024 because we will have more bits than we will kilobits representing the same value, same magnitude. Then to jump over to bytes, we have less bytes than we have bits, so we'll divide by 8. Then we have less kilobytes than we have bytes, so we divide by 1024. We have less megabytes than we do kilobytes, so we divide by 1024. And we'll have less gigabytes than we have kilobytes or megabytes, so we'll divide by 1024. Make sense? Okay, so now going back to this guy right here. So 2 classes ago, I think we were talking about primitive type values, and these are coming from a very old programming language like C that all of our modern languages have inherited. And we talked about how we have, in this case, 4 different ways of holding signed whole numbers. Signed meaning positive and negative values. So I mentioned that a byte is 8 bits, and we just had that reinforced by looking at switching between bits and bytes and kilobytes and kilobits and all that jazz, right? Then we have this 16-bit number and a 32-bit number and a 64-bit number. Okay, and you can go bigger than that, but most of our modern languages stop at 64 bits. And then if you need something larger than that, we go from there. Now, where you've maybe seen some of these words before, this bit measurement before, is with an operating system. Maybe you have a 16-bit operating system, or a 32-bit operating system, or a 64-bit operating system. Or with computer processors, maybe you have a 32-bit processor or a 64-bit processor. Or maybe with your video game systems. You know, for those of you who are into games and, you know, you like the old school stuff, the 8-bit, remember 8-bit games like Atari and stuff like that? Okay, so, you know, much, you know, less variation in color. You have less colors and stuff to work with because it's 8 bits. We'll talk about what that means. Then you had the 16-bit machines and the 32-bit machines, and 64-bit machines is what we have right now, right? All right, so what does all of that ultimately mean? Well, if you're dealing with Atari, which is 8-bit graphics, that means that you use an 8-bit number to represent each color. That's what it ultimately translates into. So that means you have, for 8 bits, you'll have 32,768 colors. No, you'll have 256 colors, rather, for 8-bit. You'll have 32,768 for 16-bit. But let's see how that all comes out, what that ultimately means. So let me jump here. We'll call this bit values. So like an 8-bit value will be a value made up of 8 zeros and ones. Okay, so for example, the number 2 in 8 bits is that. And I'll talk about why that's the number 2 shortly. So this is the 8-bit value 2. The 16-bit value 2 is that. Same exact value, we're just representing it with more zeros and ones. 32-bit value, rinse, lather, repeat. Just keep putting more zeros in there. Okay? So now we need to understand, why is this the number 2? So we want to talk about converting.
How many zeros are there?
16 or 8. So this is going to be a total of 16 bits. So we're going to have 14 zeros followed by a 1 followed by another 0. So a total of 16 zeros and ones for a 16-bit number. And what that ultimately means is that the largest number we can represent in 8-bit values is 8 ones. The largest value we can represent in 16-bit values is 16 ones. 32 is 32 ones, so on and so forth. All right, so let's convert from binary to decimal. Okay, so decimal, that's us. That's base 10, right? So decimal is base 10. Binary is base 2. So we want to convert from a base 2 number to a base 10 number, because we like base 10 numbers. 1, 2, 3, 4, 5, scales of 10, right? Computers like base 2 numbers because of binary logic, digital logic, on, off, 0, 1. All right, so if we have a value, for instance, I showed you the value 2. I'm telling you that's the number 2 in binary. So now we need to figure out why is that the number 2 in binary. Now, first of all, I would have to tell you that that guy is written in binary. Usually that's done with either like a little b there at the end of it, or I might just say in binary. Because technically, if you just saw this number, it could be like a really weirdly written 10. Make sense? Okay, so you have to know what base it was in. Otherwise, it could be ambiguous. That'll make sense as we go on. Maybe you've even seen the T-shirt before. It's like a T-shirt that says there are there are 10 people in the world, those who understand binary and those who don't. So if you know binary, you understand that this is the number 2. If you don't know binary, you read that as a 10. That means you don't know binary. Make sense? How many of you have seen that shirt before, or a bumper sticker, or somebody who had it maybe tattooed on their face? None of you know any of those people that took a tattoo like way too seriously? Like they lost some bet and they put it in like a way too public of a place, and it's like something that was like, it was funny once and now it's like stuck. I got a couple of buddies from college that still are like that. It's kind of, all right, so this is that weird saying. But now let's understand, why is this the number 2? Now this guy's the number 2 no matter how many zeros I put in front of it. Okay? Because those zeros are meaningless, and that'll make sense once I show you how this conversion works. Okay? So I'm gonna put some spaces here. All right, so I just rewrote my number, so it was some more spaces. All right, so this guy is 2 to the 8th. I need some more spaces, it looks like. This is 2 to the 7th. This is 2 to the 6th. 2 to the 5th. 2 to the 4th. 2 to the 3rd. 2 to the 2nd. 2 to the 1st. All right. Or this is the 1s place, the 2s, the 4s, the 8s, the 16s, the 32s, the 64s, the 128s. So this is the 128 place, 64s place, 32, 16, 8, 4, 2, 1. And I actually wrote this wrong. This is 2 to the 0. This is 2 to the 1. This is 2 to the 2. 2 to the 3. I should have started at the right, but I didn't. 2 to the 4. 2 to the 5. 2 to the 6. And 2 to the 7. All right, so 2 to the 0th power is a 1. In fact, I'll say any positive number to the 0th power is a 1. That'll be important because right now I'm teaching you how to convert from binary to decimal. This exact same approach works for converting from any base to decimal. And we'll see that as an example after we do binary. So it's not like you have to memorize 30 different ways to convert values. Because in computers, we typically have 4 different things that we use for numbers. Decimal, because humans are involved. Binary, because computers are involved. Octal, you'll understand why at some point in this class. And hexadecimal, base 6. Octal's base 8, hexadecimal's base 16. Okay? So 2 to the 0 is 1, 10 to the 0 is 1, 16 to the 0 is 1, anything to the 0 power is 1. Now notice that as I walk from right to left, I just keep multiplying by 2. If I was doing this for base 8, I would multiply by 8. If I was doing this for base 10, I would multiply by 10. The ones place, the tens place, the hundreds place, the thousands place. Okay? So this is the ones place, times 2 is the twos place, times 2 is the fours place, times 2 is the eights place, so on and so forth. Okay? Then the way you ultimately convert this number is you multiply the place times the value at that place, and then sum them all up. So this is 0 times 128 plus 0 times 64 plus 0 times 32 plus 0 times 16 plus 0 times 8 plus 0 times 4 plus 1 times 2 plus 0 times 1. I think we could do that math in our head, but just since we had it out there, that's the number 2. That make sense?
Wait, so why is that? Why did you change it to 1 times 2 at one point?
Because this guy here is a 1.
Yeah.
There's a 1 there, and this is a
oh.
2. So it's 0 times 128 plus 0 times 64 plus 0 times 32 plus 0 times 16. So whenever really, we wasted our time any place we had a 0 here, right? So we really could have omitted a lot of these things.
Makes sense.
So for instance, if I had a 1 here, this is 64 plus 2, which is 66. So this number right here is the decimal number 66 written in binary. Make sense how that works? So here I'll update this just so you see that we have an extra 1 in there. All right. Questions on that? Now, if I had a 16-bit number there, after 128, it would be 256, times 2 is 512, times 2 is 1024, times 2 is 2048, 4096, so on and so forth. Just keeps doubling. All right? So understand that the largest value we can store in an 8-bit number is 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1, which is 256. Make sense? That's the largest magnitude we can have for 8 bits, but that is unsigned. So unsigned, which means can only hold positive numbers. The maximum value, so this is 0 to 256. Actually, it's 0 to 255. 256 unique values. So if you do 128 plus 64 plus 32, you do all that, you'll come up with a 255. Well, you have 256 unique values, including a 0. But if we made this a signed number, can hold positive and negative numbers, then it's negative 128 to positive 127. Still 256 unique values. But what I'm doing is we are using the far left bit to store the sign. So we actually only get 7 of the bits for magnitude, for the size of the number. So we can say it's plus or minus 2 to the 7th power is what we can hold in a 8-bit number if we want to hold signed values, positive and negative values. Now, when you take the 325 class, Computer Organization and Architecture with me, we explain the various approaches for encoding negative numbers in a binary value. So I'm not going to talk about it in here, but it's a little bit more complex than just using the far left bit for positive or negative. We actually do something called 2's complement to encode it. But even if we use just the far left bit, which is something called sign and magnitude, we still get 256. We get 255 unique values, and then we get 0 represented twice. We have a positive 0 and a negative 0 then, which we're going to say is not efficient. So we encode in something called 2's complement to give us a single representation of a 0. Therefore, we get an extra value on the negative side, hence the negative 128 to the positive 127 for 256 total unique values. Make sense? For a 16-bit value, we get 65,536 unique values. So that is negative 30. Well, here, let's just write it in here. You should know the range of values that will fit in a byte, 8 bits. But I don't want you to go and memorize these values. Okay? But you should be able to calculate them. So for instance, how did I get 256? That's 2 to the 8th power. Make sense? How did I get 65,535? 2 to the 16th power. 65,536. 60 unique values, 0 to 65,535. Okay? So take it to the next one. You want 32-bit. It's roughly 4.2 billion. 2 to the 32. Then the next one is like 16 quintillion or something like that. 2 to the 64. So scientific notation, bunch of, keep moving the decimal point, big number, okay? So 16-bit, if we say unsigned, this is 0 to 65,535. Signed, this is negative 32,768 to positive 32,767. Except I should type what I say. That. For a total of 65,536 unique values that can be represented with 16 zeros and ones. That make sense? All right, so that kind of goes back to our discussion from a couple of classes ago where I said, why do we need to have so many different ways of representing signed whole numbers? Well, we have an 8-bit way, a 16-bit way, a 32-bit way, a 64-bit way. And remember, from back in the old days, memory used to be really, really, really expensive. So making that decision between holding something in 8 bits versus holding something in 16 bits could be a very expensive decision. That makes sense? And I would say it's fairly common for us to have a program that loops through and does something 10 times or goes through and does something 100 times. And 10 or 100 would fit comfortably inside of a byte. Bytes go negative 128 to positive 127. So anything in that range will fit inside of a byte, fit inside of 8 bits. So it would be in our best interest not to store that in a larger, what would be called a bit space. If you have the number 1 through 10, you don't want to store that in 16 bits. You're wasting a whole lot of space. You just have a whole bunch of zeros, and then your 8, your 1, 0, 1, 0. That's a 10. So a 1 in the 8th place, 0 in the 4's place, 1 in the 2's place, and 0 in the 1's place. 8 plus 2 is 10. All right, so back then you would have wanted to be as efficient as possible. Today, memory's cheap, we don't care. So 99% of the time as a programmer today, we would store something as an integer, 32 bits. It's like, oh, well, it's a waste of space. Yeah, whatever. We'll just waste the space, and most of our modern languages have something called automatic garbage collection anyways, where once we're done using that space, it just reclaims it and sets it aside for somebody else. Doesn't matter. Okay? And if you want to put this in some context using a skill we learned today, or learned last time, I guess. (32-bit ints) today. So I think we decided that as a low end, all of our machines have at least 4 gigabytes of RAM in it. Really, most of the machines today probably have 8 gigabytes, but at least 4 gigabytes of RAM. So 4 gigabytes of RAM is equal to how many bytes? So that would be 4 times 1024 gets me megabytes, times 1024 gets me kilobytes, times 1024 gets me bytes. So that is 4.2 billion. That's this number. Okay? Now, if we have a bunch of 32-bit integers, 32 bits is 4 bytes, correct? That is 32 divided by 8 to go from the bit side to the byte side. So 32 bits is a 4-byte number. So an integer is 4 bytes big. So that means we can store this guy divided by 4 unique integers in our budget pleaser 4 gigs of RAM. So a billion, we can store a billion integers. So even if you take some computer program that you perceive is really, really, really complex, like Windows or some video game or something like that, remember, the way human beings solve problems is we use our memory, we ask questions, and we do repetition. Even in the most complex problem that as a human being we could solve with a computer programming language, we're not going to have to remember 1 billion numbers. Make sense? We got room to play with is the punchline. Now, keep in mind, you also have other programs running on your computer. So you don't have that full 4 gigabytes of memory just sitting there waiting for you to use it for your single Python program you're going to write. All right? But realistically, since most of your machines have 8 gigs of RAM, and at any point in time you're maybe only using 2 or 3, you probably do have more than 4 gigs of RAM sitting there vacant. So as long as you're not going to go over 4 billion integers, or I'm sorry, 1 billion integers that you need to remember, you're safe. So we don't need to be that careful today. Does that make sense? Okay. So do we kind of understand what this slide is showing? This is the amount of RAM that our common lower-end computer has today, or our common higher-end computer from 5 years ago might have had, probably more than 5 years ago, but whatever, ballparky. So this is the number of bytes that 4 gigabytes equals. And if an int is 4 bytes big or 32 bits big, this is how many integers we can store in that amount of RAM. A lot. If you're writing a program where you have to remember that many different integers, so consider that's like, let's just, in our quick little example, let's assume that every one of the phone numbers for your friends is a 32-bit value. Okay, you don't have a billion friends. And even if you did, you wouldn't want to memorize all their phone numbers. chances are most of you in here know like less than 3 phone numbers from the top of your head, and one of them is yours, right? Other than that, you're asking Siri or something to like call so-and-so, or you just find the picture of them. You know, we're a lot better at recognizing somebody. We might not even know their name. So there's probably a bunch of you in here who would like become friends in the first, semester of school or something like that, and you run into people in the cafeteria and you know them, but you have no idea what their name is. It's like, hey, what's up? It's Tim, James, I don't know. It could be whatever. Okay, questions about that stuff? So we understand this idea of bits versus bytes versus kilobytes, gigabytes, gigabits, all that stuff. That was for today's quiz. And we understand the idea of converting from a binary number, a base 2 number, into its equivalent decimal number. Go ahead.
I'm a little bit confused on the difference between signed and unsigned. Like, what makes something signed?
Okay, well, in real life, if I ask you to remember the number -7, you're going to have to store that in your head as a signed number. It has to be able to hold positive and negative signs. And if you have an 8-bit value, so let's say inside your brain, I'm asking you to remember this number, -7, you're going to store that in a little 8-bit bucket inside your head. Now, because I've asked you to store the sign of that value, you're going to use one of those 8 bits to remember that negative sign. So only the other 7 bits are used for the value. So that's 2 to the 7th power for the value you can hold. So if I'm allowing a computer to store positive and negative numbers in 8-bit space, I only get 7 of those bits for holding the value, because I'm reserving one of those bits for the sign. Whereas if I'm saying, hey, look, I don't know how to store negative numbers, then I get all 8 bits to hold the value, the magnitude. Does that make sense? Usually in our languages today, if you go back to an older language like C and C++, you actually had the ability to define signed versus unsigned values. Actually, by default, it was the signed value. So by default, everything's positive and negative. But you could explicitly say, I want to store an unsigned value to give yourself a little bit bigger value, since you knew it was never going to go negative. Today, just everything's signed. Yeah, so this is more of a theory thing than a in practice thing, but just understand that if you need to keep track of positive and negative, you lose a little bit of storage capacity to keep track of that sign. Another question? Okay, so we've seen how to convert from binary into decimal. So in this little example here, we got the number 66, right? I went and added this 1 up here to give me a little bit bigger number. Okay, so that was 1 times 64 plus 1 times 2. That gave me a 66. So now let's say, what if I want to convert 66 into binary? I want to go the other direction. Decimal to binary. So I have the number 66. And I want to convert this into its binary equivalent. Okay. Question: how many of you in here had 3rd grade math? Most of us, right? Okay. Remember long division?
Yeah.
Favorite? You loved long division? Long division is actually something that's extremely important in computer science. We use it in almost all of our encryption algorithms. All your phones, when it boots up and it says this thing is RSA, 256 bits secured, that's used in long division to pull that off. Okay, and we're going to see that by example here. All right, so the way we convert a decimal number to a binary equivalent is we take our starting point. So in this case, it's the 66. We divide it by 2. Okay. 66 divided by 2 gives me a 33. All right, so now let's go and think about this in terms of long division. All right, so I did 66 divided by 2 in long division. What would I get? I would get a 3. 3 times 6 is 18, right? So 66 divided by 2. The 2 goes into a 6 3 times, so we record the 3. 2 times the 3 is a 6. I wish I could draw my little long division thing here. Let's just do it. This should bring back the good old days. Then we have our 66 in here, and we are dividing it by 2 out here. So 2 goes into 6 3 times. 3 times 2 is 6. Like this. 2 goes into 3 how many times? 3 times? I'm shortcutting this a little bit. 66, subtract, we get a 0. So this is remainder 0. Remember that guy?
Yeah.
Okay. So what we do here is we record the remainder out here to the right. So this is going to be a remainder of 0. Now, if I divide any number by 2, what are the possible remainders I can get?
33 is negative.
Any number divided by 2 in long division, what are the possible remainders I could possibly have? 1 or 0. Can I have a remainder of 2? No, that means I did bad division. Because if I have something divided by 2, if I had a remainder of 2, that means that number 2 actually went into it another time, right? I did bad division. Okay, you can't say 6 divided by 2 is 2 remainder 2. It's 3 remainder 0. Make sense? Okay, so I'm going to record the remainder, then I'll record quotient. 33 divided by 2. That is 16. 16 times 2 is 32. Remainder 1. I have 1 left over to get me back to a 33. So 33 divided by 2 is going to be 16, remainder 1. 16 divided by 2 is 8, remainder 0. 8 divided by 2 is 4, remainder 0. Oh, let me stretch this back down here. 4 divided by 2 is 2, remainder 0. 2 divided by 2 is 1, remainder 0. 1 divided by 2. How many times does 2 go into the number 1? 0 times. Doesn't fit. 0 times 2 is 0 with 1 left over. Then we read our answer from the bottom up. So this is 1, 0, 0, 0, 0, 1, 0. This is the binary version of that number.
For the last one, 2 goes into 1 0 times with the 1 remaining.
Correct.
So you get that 1.
Yeah, but I mean, the reason I got the 1, I mean, this wasn't some sort of special case. So 2 went into 1 0 times, so that I take 0 times 2, which gives me a 0, and it takes 1 extra to get me to the 1 that's over here. Yeah, so exact same pattern. I'm not doing something special there on the end. Okay, but I do know that I'm finished when I finally get a 0 down here. I've whittled this guy down to nothing, so I now know when I have a 0 there that I have my final number, reading it from bottom up to the right, and my number was made up of remainders. That make sense?
What's the pattern again?
So you take your starting number, divide it by the base you're trying to convert it to. In this case, we're going to binary, so I'm dividing it by 2. You record the quotient, and you record the remainder. Take your quotient, divide by 2, record that quotient, record the remainder. Quotient divided by 2, record the quotient, record the remainder. Then at the end, you read your remainders from bottom up, and that's your answer. So this number should look very, very similar to this number. What's the one difference? Is I have an extra 0 here, but 0 times 128 is 0, so that doesn't impact the number, right? So what I actually end up with here is, this is 1, 2, 3, 4, 5, 6, 7. This is a 7-bit representation of the number 66, because I actually only need 7 bits to represent 66. If you're asked to show the 8-bit version of that, just tack an extra 0 on the front. Doesn't change the value of it. If you're asked to show the 16-bit version of that, tack another 8 zeros on the front. So on and so forth. Okay, because this is 0 times whatever plus 0 times whatever plus 0 times whatever, blah, 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 until we finally get to 1 times the 64's place. Make sense? So when you take this approach, you'll always get the most efficient representation of the binary number. We're not going to just keep dividing when we just have a whole bunch of zeros trailing. So this tells us when we're done, and we actually only needed 7 total bits to represent this number. Okay, so from a human perspective, we would say, I can represent the decimal number 66 in 7 bits. In computer speak, all of our memory sizes are powers of 2, because binary, digital, on, off, blah, blah, blah. So our smallest bucket of memory in our computer is 8 bits. So to store a 66, we would store it as 0, 1, 0, 0, 0, 0, 1, 0. That's how it would actually be stored. All right, that makes sense? All right, so just real quick, let me just show you. I mentioned the pattern's identical, right? I'm going to take this number. What if I wanted to turn this into octal? So instead of decimal to binary, it's decimal to octal. And octal is base 8. You don't even have to know why you would ever need a base 8 number. I'm just saying, turn a base 10 number into a base 8 number. Go. Okay. Now we know in base 2 numbers, binary, the legal values are 0s and 1s. In a base 10 number, our counting system, our legal digits are 0 to 9. The base minus 1. 0 to the base minus 1. So in octal, legal digits are legal, they're called octets, is 0 to 7. All right. So let me back this up here. So now instead of dividing by 2, I'm going to divide by 8. Let me just get rid of this guy in here. All right, so 66 divided by 8 is an 8. 8 times 8 is 64, remainder 2 to get me to a 66. 8 divided by 8 is 1. 1 times 8 is 8 with remainder 0. How many times does 8 go into 1? 0 times. 0 times 8 is 0 with remainder 1. We know we're done because we have a 0 there. Final answer, reading it from bottom to up, 102. So 102 octal is equal to 66 decimal. See how that worked? Identical pattern.
Yeah.
All right. Questions about that? All right, I am going to assign the next section from the book, so I think it's 1.6, right? Last one you did is 1.5. Also, be prepared for a quiz on this next class for converting either from decimal to binary. I won't have you do octal. Let's just keep the pattern simple. Decimal to binary or binary to decimal. Should be able to go either way or maybe even both ways. All right, make sense? Hopefully, though, I just proved to you that you're not learning how to convert decimal to binary. You're learning how to convert decimal to any base. Similarly, that original pattern is from any base to decimal. Same exact algorithm works. All right, I will see everybody on Wednesday.